Okay, so that's what we were talking about last time. We were talking about this idea of suppose we have a linear transformation, right? Linear transformation is they come in all sorts of shapes and sizes. Some of them are pretty weird and unwieldy, hard to deal with, hard to write down. Certainly inconsistent in how we write them down, right? They come in a lot of different ways of looking. So the big idea is, just like we did with vectors, can we find a way to use bases for the domain and target, perhaps, to rewrite the linear transformation as a matrix? Right? And the nice thing about a matrix, aside from being compact and numerical, is all matrices are, roughly speaking, they all kind of look the same, right? So we can have consistent and convenient ways that we can develop for how to deal with matrices, and therefore a consistent way of dealing with all kinds of linear transformations all at once. Okay, so it's a really nice idea. The punchline is that yes, we can do this. There is such a thing, this matrix, right? And we wrote down a formula for how to compute it. Right here, saw some examples last time, but you can find this matrix by columns, one column at a time, and you get those columns by taking the input basis vectors, applying the linear transformation to them, taking those results, write them as coordinates with respect to the output basis. Okay. All right. So we talked about that last time, and now I want to just talk about a special case of this. And let's talk about what happens if our domain and target are the same space, and if we use the same basis, script V, for both. Now this is just a rewrite of that formula with this special case in mind. And so again, we compute it one column at a time. You take the input basis vectors, those are these. You do the linear transformation to them. That's that. And then you write the results with respect to the output basis. Well, that's the script V basis again, right? And here's what we end up with. We end up recovering a statement that is a generalization of an observation that we made a long time ago. Well, I say a long time ago. So at the start of section 5.3, way back at the start of section 5.3, we observed that every linear transformation from Rn to Rm is a matrix. And furthermore, the formula for that matrix was the columns are the images of the standard basis vectors. Okay, so I claim that what we have here is really just a generalization of that fact. Notice the columns are the images of, well, let's see here. Well, the basis vectors. I'm going to just say the basis vectors. Now, which basis vectors? Well, the input basis, whichever basis you're using, of course, right? Now, how do you take vectors and make them columns? Vectors are abstract things. Columns are arrays of numbers. Well, we write with respect to, of course, the output basis. Same basis. Script V. Right? So, really, this is kind of the same statement that we had in that special case, the sort of Euclidean special case from last time. It's just that now the columns are the images of your basis vectors, whichever basis you're using. So here's why it's a special case. Let's think about what happens if this script V basis is the standard basis for Rn. This statement becomes, that formula becomes, the columns are the images of the standard basis vectors. Of course, written as coordinates with respect to the standard basis, because at that time, that's how we were writing all vectors. So again, that old statement that we saw at the very start of section 5.3 is a special case of this this formula here, or another way to say it is this is a generalization of that fact. Okay. Alrighty. Here's an example. I like this example. This is a little bit of a slightly incomplete example. Hopefully by the end of today we'll be done with enough that we'll be able to actually finish this example. But let's get started anyway. Suppose I want to describe this linear transformation that flips vectors in R2 over this line x equals 2y. So the linear transformation does that. We'll just flip over that line. how would we write down a matrix that represents this linear transformation? And I'll point out this is kind of a hard question, because if you think to yourself, well, I'll just we'll write everything with respect to the standard basis. We know the columns or the images of the standard basis vectors. Let's just think about what does this flip do to E1, for example. What does that flip do to E2? And we'll make those our columns and be done with it. The problem is, this line that we're flipping over is a weird line. This angle that it makes with the x-axis is a weird angle. It's not pi over 6. Right? It's, it's, arctan of a half, whatever that is. So, it's a hard problem, right, geometrically. So, here's a better way to represent this linear transformation, and that is pick a different basis. There's no law that says we have to understand everything with respect to the standard basis. I'm going to pick instead this basis consisting of these vectors that I'm going to call V1 and V2. So I'm going to pick that basis. Now I can tell you what these vectors are. I mean, I understand the geometry of this line, a certain amount of x is equal to 2y. Not hard to persuade yourself that a vector parallel to that line is 2, 1, right? And a vector perpendicular, let me make clear that that's perpendicular. Vector perpendicular, think back to old math 212 formulas, is -1, 2. Okay, I claim this is a great choice of basis. Understanding what the linear transformation does in the language of this basis is actually going to be a pretty straightforward problem. Using this idea here, the columns are the images of the basis vectors. So let's just look at the images of the basis vectors. What does our linear transformation do to our newly chosen basis vectors? And it's going to turn out it does some really simple things. This first one, for example, what happens when you take that V1 and flip it over that line? Well, it's sitting right on that line. And when you flip it, nothing happens. T of V1 is V1. Similarly, what happens when you take that vector V2, flip it over this line? Well, it's perpendicular to the line. When you flip it, it's going to end up pointing exactly in the opposite direction. Its flip is going to be the exact negative of itself. Yeah, everybody on board? Now, what are these images with respect to the standard basis, you may ask? And I'll point out, who cares? We don't need to know what those vectors are with respect to the standard basis. We're not using the standard basis. We've picked a basis to use for both the input and output. What I need to know is how to write those images with respect to that basis, not the standard basis. Who cares about the standard basis? We've gone to some trouble to conveniently be able to avoid the standard basis, right? Okay, so how do I write those? What are the coordinates of these outputs with respect to script V? I've got to figure out how to write these images as linear combinations of V1 and V2. Right? What are these coordinates here? And I think it's not hard to persuade yourself that V1 is 1 V1 plus 0 V2. And these numbers, 1, 0, then become my first column. Likewise, negative V2 is 0 V1 plus negative 1 V2, and these numbers become our second column. So with respect to the standard basis, I don't know, but with respect to this other basis that I've conveniently chosen for myself, this act of flipping over that line is really easy to represent as a matrix 1, 0, 0, negative 1. Right, so nice choice of basis. Good general rule to keep in mind is if you're trying to understand a linear transformation, pick a basis where it's easy to find the images of those basis vectors, and ideally where those images are easy to write in terms of those basis vectors. So pick vectors that are naturally, conveniently, arranged with respect to the transformation you're looking at. Okay, yeah.
If you chose a different basis, would you get the same result in the matrix?
Well, so this would not be the same. So what we have here depends on what basis that I've chosen. And here's where I'm going to have to confess. My example here is a little incomplete. One could say that, well, maybe what I really need is to understand T with respect to the standard basis, right? I mean, if you really need that, right? So, so we've got an answer that's dependent on our basis, and you're quite right. If you pick a different basis, you're going to get a different matrix. So what I really need to make this example really complete is how would I convert this information about T with respect to the V basis? How would I use that to rewrite to get T in terms of the standard basis? And we're not ready to do that just yet, but we will be by the end of today's class. Fingers crossed. Yeah. Okay. All right. Okay, so this next thing I want to talk about, this is not in the book. This is something that I think is valuable, and I'd like to talk you all through this. I made up this example, and I just think it's a nice example. And it points to a certain point of view on this kind of stuff that I want to encourage everybody to try to get comfortable with. I'm going to start this example by laying out a bunch of notational choices. I'm just going to enumerate some things. Everything that I have here on the screen now is nothing's really happening in any of that. This is just suppose I have this, suppose I have that, and labeling things with names. So we're going to start off with a linear transformation from V to W. Let's say the domain is a vector space, of course. Suppose I have a basis for it. I'm going to call that basis S1. By the way, I do not mean it's the standard basis. V is a vector space. No reason to believe that it's Rn. Right? There may be no such thing as a standard basis. I guess I'm calling it S for familiarity purposes. Okay. And suppose I have another basis consisting of vectors V1 through Vn. I've got two different bases now for my domain. Okay. Now let's look at the target. Same deal. I can talk about one basis. I can talk about another basis. Let's just give these names. Okay. Now, for no particular reason other than I needed to have something to refer to here, I'm going to talk about this vector, V1. I'd like to tell you what that vector is. I'd like to tell you its coordinates. If I'm going to tell you its coordinates, I have to tell you its coordinates with respect to some basis. Right? So I'm going to tell you its coordinates with respect to the only other basis that I have. Namely, I'm going to tell you its coordinates with respect to that S basis. And let's just say, again, so that I can have something to work with and write down, let's say its coordinates are C1 through Cn. Okay. Likewise, let's say this vector W1, for whatever reason, I want to tell you what it is. I have to tell you its coordinates with respect to some other basis. Let's choose that basis, for lack of other options. And let's say those coordinates are D1 through Dm. Okay. Nothing's happened yet. I haven't done anything. I've just labeled some things. Okay. Now, here's another thing I can do. I've got this linear transformation T. Keep in mind, we can describe linear transformations with respect to a choice of bases. Let's describe T first with respect to the S1 and S2 bases. Right? So S1 basis for the domain, S2 basis for the target. With a linear transformation and a choice of bases, I get a matrix. I'm going to call that matrix A. I haven't really done anything. Let's just say, suppose that's what it's called. Similarly, this linear transformation, I could describe it with respect to V and W. Right, same linear transformation. Describing it with respect to V and W, I get some other matrix. We'll call that M. Okay. All right. With all of this set up, all I want to do with this example is show you different ways that the same statement might come at you. right? So that you can kind of know in some sense what to expect, and then how to think about statements that you might see about objects such as we've discussed here. So let's look at this statement: T of V1 equals W1. Before I go on, let me emphasize, I'm not saying that this is always true. I'm not saying that whenever you have a linear transformation, the first basis vector goes to the second basis. No, of course not. Right? Let's just suppose in this example that it is, and let's talk about how to make this statement. What are the different ways in which you might make this one statement? Here, finally, are the statements I want to talk about. These 5 statements all say the same thing. This is pretty weird to look at, but that statement right there ultimately, morally, says the exact same thing as that statement right there. Now, this is very surprising at a glance. The top statement up there seems to be making a statement about what some matrix A is doing. This bottom statement doesn't make any reference to A. The top statement refers to some vectors with C and D coordinates. This doesn't make any reference to C's or D's. This is just ones and zeros. So they seem to be making statements about completely different things. Here's how I want you to make the connection to realize that they're kind of really both saying the same thing, as follows. Let's start with this top statement. What does that mean? How do I think about it? We will start with A itself. A, what do we know about A? A represents the linear transformation T. More specifically, it represents the linear transformation T with respect to a given pair of bases, S1 and S2. So A is representing T, and it is furthermore telling you in some sense what language we're speaking when we make this statement. We're representing T with respect to S1 and S2. That means that inputs to the linear transformation T, thinking of this as a matrix, I'm interpreting the inputs as being coordinates with respect to S1. So this right here, the fact that there's an S1 there, that's telling me that this thing that we're multiplying this matrix by, that's the S1 coordinates of something. So that's our foot in the door to then ask, okay, this is the S1 coordinates of what? Well, those numbers are the S1 coordinates of V1. Yeah? Okay. Along those same lines, again, we're representing T here with respect to this pair of bases. The output basis is S2. That means that when this matrix multiplies by something, what is going to come out will be the coordinates with respect to S2 of some output vector. So that's telling me then, this S2 is telling me that these numbers are S2 coordinates of something, and then we look back up here again to our notational choices, and we see that those are the S2 coordinates of W1. So all together then, this statement, this seemingly numerical statement about matrix A and coordinates C's and D's, this numerical statement is a statement in the language of these chosen bases S1 and S2, and ultimately what it's saying is T, in that language, applied to V1, in that language, gives me W1, in that language. In other words, in S1, S2 language, it's telling me T of V1 equals W1. All right, so I think it's an important line of reasoning to look at a numerical statement and realize from what's written down and from what you're given, right, to realize that that's actually not just a numerical statement. This is telling you something in a certain language, with respect to certain bases. It's telling you a statement about a linear transformation and some vectors, and to interpret, identify what is the. Again, I like the metaphor. What is the language being spoken in this statement? And in that language, what is being said? Okay. All right. So now you can do the same thing for the statement down here. Let's do the same thing here. We've got this M thing. What is M? Well, M, again, is telling you about T. That's what our choice was for what M is. M represents this linear transformation T. With languages being V and W, input vectors are to be understood as representing vectors with respect to script V. Output vectors are to be understood as being in the language of script W. So that means, so this V here means that these numbers, 1, 0, 0, 0, 0, are V coordinates of something. And then here you can come up here and ask, do we see the numbers 1, 0, 0, etc. up here? And we don't. So we're going to have to figure this one out on our own. What vector is it, we ask here? What vector is it whose coordinates with respect to the basis script V, whoops, oh man. Yeah, plus. So, what vector is it whose coordinates with respect to the script V basis are 1s and 0s? Well, let's put those coordinates in there. A 1 there, a bunch of 0s everywhere else in the list. Not hard to persuade yourself we're talking about just V1. So, this statement here is the same as this statement here. Everybody see how I reverse engineered that? Any questions? By the way, heads up for the occasional convenient linear algebra problem. This question that says, how am I going to, morally what this is saying is, how am I going to write V1 as a linear combination of a list of vectors that includes V1? And so that's a freebie, right? If V1 is in your list, well then take one of that, nothing of everything else, and bam, there's your V1. We always know that there's a unique way to write something in coordinates, and so if you find a convenient one, that's the only one, and there you go. So always be on the lookout for lucky breaks like that. Okay, analogously for the other side, this is script W coordinates of something. Script W coordinates of what? Well, easy to persuade yourself, W1. How do you write W1 as a linear combination of these script W vectors? Well, it is 1W1 plus nothing else. Okay, so again, this statement, now it looks like an arithmetic statement, but not really. I guess it's an arithmetic statement, but keeping in mind that M is understood to be telling you about T. This is actually telling you about a linear transformation. It is telling you about a linear transformation in a certain pair of languages. That tells you what languages these are with respect to, then you can figure out what vectors are being described. And so again, you get the same statement. So ultimately what we have here then, we have these two pieces of arithmetic, different matrices, different lists of numbers. They don't seem to have anything to do with each other, but understanding with respect to our conventions up here, we find that both of those statements are really saying that same thing. Okay, so what I want to encourage y'all to do, there's a lot, I'm throwing a lot at you here, right? There's a lot of notation. There's a lot of ideas running around here. Try to make sure that you are comfortable in realizing that statement is about arithmetic is really this statement about linear transformations. Likewise, that this statement about arithmetic is really the exact same statement in the different choice of languages of different bases, and therefore these two statements themselves are equivalent. Okay. I see a hand somewhere? Yeah.
So to go from like the second step to the actual third step,
yeah.
Is that more just the square argument? Is that where that one's coming?
To go from here to here?
Yeah.
This is just sort of an intermediate step where I'm recognizing that that this A is really representing T, but with a certain choice of languages. And here I'm just the third statement. I'm just saying, well, let's say T of V1 equals W1, but without any choice of bases. Let's just say it in the abstract.
Oh, because
Yeah, that's right. Yeah. Okay. Yeah.
Does that mean N is the identity matrix?
No, so not quite. So what it means is, and I hear where you're coming from. What it means is that M, its first column, looks like the column of the identity matrix. But what's over here is a big who knows. Yeah. Does that make sense? Okay. Alrighty. So something to digest. Give yourselves plenty of time to think that through. Okay. All right. Here is a related question. Suppose you know the coordinates of a vector with respect to some basis. And suppose that you instead would like to understand that same vector with respect to a different basis. Now I emphasize, you're not talking about rewriting the vector. It's still the same vector V. I don't want to change the vector. I just want to translate it into a different language. How do you translate vectors, you might say, right, from V language into W language? So here's a brute force unrecommended thing that you could do. You could take these coordinates and you could multiply it all out and identify what is that actual vector V. And once you know that actual vector V, well, then there is a whole process by which you can find its coordinates with respect to W. Right? So that's the brute force way to do it. Recover V, find its coordinates with respect to W. Tedious. What if you need to do this a bunch of times? Wouldn't it be nice to automate this process? Here's the clever way to do this. Realize that I can choose to view this as the action of a linear transformation. We've got a couple of different bases there, script V and script W, sure. But ultimately, there is a linear transformation here where I'm taking an input vector and getting an output vector. It's just that this is a really boring linear transformation. I'm not changing V. And that's a linear transformation. So the action of don't do anything is linear. It's a little silly, but this is true. So I think this is a nice exercise. I want everyone to take a few seconds, a minute, whatever, and persuade yourself that this is true. The action of doing nothing is a linear transformation. Show that the action of doing nothing commutes with linear combinations. It's just a matter of writing it down, but it's an immediate thing to prove. Yes.
Would you call that like multiplying by 1?
It's kind of like multiplying by 1, but we don't have a multiplication on these vectors. Sure, it's scalar multiplication by 1, yeah, sure. But we don't have to think of it that way. Let's just think of it as a linear transformation where I of V equals V. Yeah, totally. Okay, so seemingly we're making a mountain out of a molehill here, right? I mean, why am I bringing linear transformations into this? I just wanted to figure out how to convert, right? The nice observation to make, though, is that viewing this as a linear transformation, what I am actually doing is I am trying to find this matrix, the matrix representing I with respect to this chosen pair of bases, script V and script W. Right? Viewing this as a linear transformation, this matrix represents the process of, to the vector, we're not going to do anything. We're going to view the input vector with respect to V coordinates, and then after having done nothing, we're going to then try to view that output with respect to W coordinates. So just observe, that's the translation we're trying to do. And good news, we already know how to find these matrices. Right? So it's a matter of writing down then. So this change of basis from script V coordinates into script W coordinates is achieved here, let me do it like this, is achieved per the formula on the several pages back by take the input basis, do the linear transformation to them, write the results in output basis language, make those your columns. Right, so that's several pages back. That's how you represent linear transformations as matrices. Good news, the action of the linear transformation doesn't do anything. So we get a particularly convenient formula here for our translation matrix, our change of basis matrix. If you want to find the columns, just take the input vectors right with respect to the output basis. That's it. Okay. All right, let me show you an example. So this example is in R2. We're going to start off with this basis script V. I would then like to convert into coordinates with respect to the standard basis, script S. Y'all remember the standard basis, E1 and E2. Let me tell you about these vectors, V1 and V2. If I want to tell you what those vectors are, of course, I have to tell you their coordinates. I have to tell you their coordinates with respect to a basis. Specifically then, I'm going to tell you what V1 is by telling you its coordinates with respect to, well, the only other basis I have, script S. And likewise, I'm going to tell you V2 by telling you its coordinates, of course, with respect to S. Alrighty, so those are my two bases, and of course you know what E1 and E2 are. So those are my two bases. If I want to find the change of basis matrix from V to S, let's use the formula on the previous page. Formula on the previous page says take your input vectors, write them with respect to the output basis, make those your columns. So let's do that. I've got to take my input vectors, write them with respect to my output basis, and make those my columns. That's the formula from the previous page. And then notice, as it turns out, those were given. Lucky break. Coordinates of V1 with respect to S, those were given. Right, coordinates of V2 with respect to S, as it turns out in this particular very convenient example, those were given. So that becomes my second column. And so there's my change of basis matrix. I claim, and we're going to see this flesh out, that matrix translates from V language to S language. The mere process of multiplying by this matrix will take script V coordinates of a vector and return to you script S coordinates of the exact same vector. Okay, now arguably a proof that this is going to work is on the previous page. We already, there's our formula. We already derived that. We don't really need to prove this. At the same time, I do want to get our hands dirty. Let's actually see this. You know, it'd be nice to have a visceral experience of, oh, look at that, it actually worked. So this is what I like to call a sanity check. So here's a sanity check. Again, the assertion is that this matrix here will convert coordinates. I claim this is going to convert from script V coordinates into script S coordinates. This is a sanity check, so I'm not going to put every possible vector in here. I'm just going to show you that this works for a given single vector. Arbitrarily, I'm going to choose V1. Notice V1 doesn't change, right? We're not messing with the vector. We're just going to take the V1 vector. We're going to write its script V representation. We're going to turn that into a script S representation, same vector. Okay, well, this one here is a freebie. I love these freebies. The script V coordinates of V1. How am I going to write V1 as a linear combination of V1 and V2? Well, it's clearly 1 V1 plus nothing else, so 0 V2. always be on the lookout for the freebies. The S coordinates. The S coordinates of V1, oh well, that was given. The S coordinates of V1 are 1 and 1. So if this matrix is doing its job, if this matrix as described is converting V coordinates to S coordinates, right, it would need to be the case that when I multiply that matrix times that vector of coordinates, that I should get this vector of coordinates. This is the arithmetic that we need to check. It's easy to check and see that it works. And so as expected, as planned, this matrix has translated V coordinates to S coordinates. How are we doing? Yes?
Was B1B a given?
No, this is the sort of clever observation I'm making. So this right here is the observation that V1 is 1V1 plus 0V2. Right? So this basis consisting of V1 and V2, right? If I want to write this vector as a linear combination of that basis V1 and V2, then the coordinates, just clever observation, the coordinates are 1 and 0. Yeah. Okay, there's another example here. I'm going to let you all read this example. This is a very, very similar example. This is just for V2 instead of V1. But notice the same thing is accomplished. We are confirming that matrix that's supposed to convert from V coordinates to S coordinates does indeed convert from V coordinates to S coordinates. It's a matter of checking that those are the V coordinates, these are the S coordinates, and then just confirm that the arithmetic actually works. Okay. Exercise for y'all. One last observation. If you want to convert back, right, if you've got a change of basis matrix from V to W, and you want to know how does that relate to a change of basis matrix from W to V, I hope it comes as no surprise that if you convert and then convert back, that ultimately you've done nothing. Right? If you take a list of script W coordinates, convert to V coordinates, then convert back to script W coordinates, it's the same exact thing. So this product of change of basis matrices doesn't do anything. And therefore this product of change of basis matrices is the identity matrix, and therefore these matrices are inverses of each other. Easy little observation. But very convenient. Sometimes you're going to find that one or the other of these is easier to write down. Such as in this case here, we got lucky, and look how easy it was to write down the change of basis matrix from V to S. That was really easy. The columns that I needed were given. Right? I mean, that was nice. Right? And so if I, let's say, needed to find the change of basis matrix the other way, suppose I needed to go from S to V, I would write this down first and then just invert that matrix. Okay. Now I have to begin an awkward discussion of terminology. The book and I have a disagreement on how to talk about change of basis matrices. And I really think I'm right on this. And, anyway, it's a subjective choice. This is an aesthetic thing, but it just, it really bugs me the way the book does it. So let me describe what I'm talking about. First, let me tell you what the book and I are in perfect agreement on. The use of this notation to represent the change of basis matrix. I'm perfectly fine with that. No problem. I mean, there's a million notations, and I don't really care. But anyway, this is the book's choice, and it's fine, so we'll go with it. No problem. We agree that converts for a given fixed vector V coordinates into W coordinates. We agree that this is the formula for computing said matrix. Here's where we disagree. I think it's pretty reasonable, see if you can follow me on this, that since we're converting from V coordinates into W coordinates, I feel like this should be called the change of basis matrix from V to W. The book sees this differently. The book, believe it or not, refers to this process executed by this matrix. It calls this matrix the change of basis matrix from W to V. Is that just me, or is that weird? Right? I mean, clearly we're going from V to W, right? Super weird. Okay, let me show you what the justification is from their side. They're not 100% wrong. There is a point of view behind their choice, and it's ultimately just terminology. So, okay, whatever. Here's another true fact about this matrix. This matrix that converts from V coordinates to W coordinates. That same matrix also does a different thing. If you multiply, instead of multiplying vectors on the right of it and thinking of them as coordinates, if you were to multiply a matrix on the left of it, color choices. If you were to multiply on its left a matrix whose columns are the W basis vectors, what this purple matrix would do is result in a matrix whose columns are the V basis vectors. And that's their point of view on whether they want to call it from W to V. Right? That's where they're coming from. Now, let me persuade you that algebraically this is a true statement. That this times that does equal to this. It's a matter of looking at it, really. But let's think about, how would I compute, for example, this column of the product? Well, that column of the product is going to be this linear combination of those column vectors. That's how matrix multiplication works, by columns. And these coordinates here, these coefficients here, this first column of coefficients, what this says right here is, how would you write V1 as a linear combination of the W vectors? That's what this says. So if you take the coordinates that make a linear combination of the W vectors into V1, and if you take that linear combination of the W vectors, you get V1. So, this works, right? And likewise for the other columns. So this works in all the columns. So, look, the book's not wrong in that sense. And let me zoom out so I can fit all this on the page. Let me remind you. So here are our two situations. So we've got, on the one hand, we can convert V coordinates into W coordinates, thus motivating the term from V to W. Or let me do it like this. From V to W. On the other hand, this statement, this same matrix doing this other task, like that, they're converting the entire W basis into the entire V basis. And so they say from W to V. Okay, does everybody see the conflict and the tension? All right, now let me tell you why I make the choice that I make. And that is, in this course, we're going to be doing a lot of this. We're going to be doing a lot of that, where we pick a vector and then change languages from V language into W language. We're going to be doing zero of this. Like none at all. Right? So, yes, this matrix does have different applications. Yes, you can interpret those, you can use those to motivate sort of different choices on the terminology, but this one here is irrelevant to Math 216. This is not going to come up. right? So we're going to use terminology that makes sense with respect to what we're actually going to be doing with these matrices, right? We're going to call this matrix the change of basis matrix from V to W because that's what we're going to do with it. Does that make sense to everybody? Okay, so the upshot, how does this affect y'all? All of my old midterms are written with this use of the terminology. All of my old final exam, well, y'all can't see those. This year's final exam that you'll take will, along with all my other old ones, will use this choice of terminology. Just be aware that when you're reading the book, they're gonna have these backwards. Right? They're going to say from W to V instead of from V to W. Also be aware when you're looking at the homework exercises. There are a few homework exercises in section 5.3 where the book uses their terminology, right? So when you see in the book's homework exercises, if they say, from blah to blah, interpret it the way that they intended it. In other words, flip it and interpret it like this. Does that make sense to everybody? Okay. All right. So I want you to interpret the book's use of the terminology as the book intends in that context, because then the answers in the back of the book will be what the book intended for them to be, and everything will sort of go according to their plan, which is fine. But anywhere outside of the book, exams, for example, this terminology is what we're going to use. I emphasize one last thing. I agree with the book completely on the notation. We're good. The formula. Cool. What it does in this context. Absolutely. None of that's different between the book and me. It's just the language. Just when they say it in English that they, I think, make a weird choice. Okay. Alrighty. So one last thing I want to get to. I want to talk about change of basis for linear transformations. Just like with vectors, we found ourselves. Where's my thing? Here it is. We found ourselves looking at a vector, an abstraction, with respect to one basis, and we want to keep the same vector. We're not changing the vector. We just want to change the basis with respect to which we talk about it. Right? So. Not changing the abstraction, just changing the language that we're using to talk about it. This is how you do it for vectors. Now let's ask the question, how do you do it for linear transformations? And so here we are again. Suppose you have a linear transformation. You can write that linear transformation with respect to one pair of bases, script V and script W, thus giving you a matrix. You can take that same linear transformation and write it with respect to a different pair of matrices. You could a pair of bases. You could write it with respect to V prime, W prime, thus getting a different matrix. And without wanting to change the linear transformation at all, we could reasonably ask, hey, if I know this numerical representation of it, but I would instead like to have that numerical representation of it, how do I do that? What's the easiest way to convert then this matrix into that matrix? And the observation to make is that this matrix can be thought of as a kind of a three-step process. It's a sort of up and over, back and over and forward, if you will. So first, convert from V prime coordinates to V coordinates. Then do the linear transformation with respect to bases V and W. And then lastly, convert the output W coordinates into the desired W prime coordinates. So no big deal. Instead of multiplication by just one matrix, you're sort of multiplying on either side by, on one side by one change of basis matrix, on another side by another change of basis matrix. And that's what that is. So no big deal in the process. Let me say a quick word about this diagram. It is usually the case that students find that diagram to be a little bit scary and intimidating. It's all three-dimensional and stuff, right? let me point out that, for one thing, you don't have to use that. If you want to think about it just in these terms, you certainly can. But it does do some nice things for you. A very quick observation. Here's a homework exercise, or here's something that's very closely related to a homework exercise. Suppose you are given t of some vector v w coordinates. Suppose you're given that and you would like to compute from it what you get when you take the v prime w prime matrix and multiply it by v's v prime coordinates. So now this looks like a hairy, nasty little problem, right? I'm given I'm not given v. Oh my gosh, right? I'm given some nasty, hairy thing, and I want to compute some other nasty, hairy thing. Look what the diagram will do for you. Just because of the structure of the diagram. That's what this says. And you can see right there on the diagram, if I'm going to take a vector, do t, and then convert to w coordinates, you can see right where that puts you. Likewise, over here, what is this? Well, that says find v prime coordinates and then multiply by that matrix. So how do you get from the purple expression to the blue expression? You can see right from the diagram really easily, just multiply by that change of basis matrix. Right? That's one change of basis matrix to multiply by. Algebraically, that's pretty hard to see. I mean, you can do it, but this is much harder to see algebraically. The diagram is your friend in cases like that one. So keep that in mind. We'll pick up here next time. See y'all later. Have a good one.